probably saw it coming that once we defined a conditional statement in the universal form, that we will talk about its relative, contrapositive, converse, and inverse. So here we go. Let us remind ourselves that the universal conditional statement starts with the for all quantifier. So for all elements x in some domain D, if P, then Q. And then, similarly to the standard contrapositive, converse, and inverse we've seen before, we're going to modify this second half of the universal conditional to match the previously defined notions. So notice that for all x in the domain stays. Contrapositive, we flip the order and negate both parts. With the converse, we just flip the order, and with the inverse, we just negate the both parts. So let's see how that works out with, first of all, a plain English translated into symbolic form. If an integer is divisible by 4, then it is even. So before we actually state the contrapositive, converse, and inverse, let's rewrite this in the universal conditional form. If an integer is divisible by 4, which means that our domain is integers, so for all x in integers, if x is divisible by 4, then it is even. Then x is even. So we can clearly see our P and Q parts here. So this corresponds to P of x, and this corresponds to Q of x. Now, let's state the contrapositive of this statement. Again, notice that the actual universal part does not change. So we will start with for all x in integers, and then we're simply going to produce the contrapositive of the second half of the statement that we have practiced in the logic unit. So here we will have to flip the order. Remember, the contrapositive flips the order and negates both sides. So not Q, the opposite of x is even means x is odd. So if x is odd, then not Q. X is not divisible by 4. And we will continue in the same manner for the inverse and the converse. I'm going to leave this for you as exercises. This is nothing new. You're simply modifying the original conditional to match the form of the inverse and converse while keeping the actual universal quantifier the same throughout. So fill this out for extra practice and to remind yourself how to do it, because the logic unit was now quite a bit back. So reminding yourselves of that would be very useful. Next up, we're going to talk about what happens if we have more than one quantifier in the same statement. So up until now, we've seen statements for all x in, let's say, integers and so on, or there exists an x in integers such that, and so on. But we've never mixed these quantifiers. In this section, we're going to practice what it means to actually use both of the quantifiers together, and we will see how the order actually strongly matters. So let's start with this first statement. For all x's in D, there exists a y in E such that some property holds. Notice that this property will depend on both x and y. We're going to think of that in terms of kind of like a game to play. Whatever x you pick, because you can pick any one of them, I can find a y that will have this property. So you are allowed to pick any x. I am going to look for the y that exists so that this property that depends on both x and y actually works. Notice here that different y's will work for different x's. So this is truly sort of a two-player game. You fix the x, and then I have to go looking for y. Let's write that down. So once again, you are allowed to pick any x you want because this is a universal quantifier, but once you choose it, I will proceed to the next step of finding the y for which this property will hold. And this y is not going to be the same for all the choices of x's. You start with the first step, and then I have to go looking for y. What happens if we flip the order? So we start with an existential quantifier and then we follow it up with the universal one. So here we're saying there exists an x so that for all the y's some property holds. So there is an x that is very special because once you found that x, the property holds for all of the y's, no matter what those y's are anymore, as long as they're within the right domain. So now I have to pick an x that will work no matter what y you choose. So I have to pick a very special type of x that will work no matter what y you throw at me. And it has to be the exact same x for all of these y's. So this is quite in contrast to the above, where once you pick an x, I had the choice of the y that will work. Here, I have to make sure that it's the same x that will work for any of the y's. Now, this is still a little abstract and theoretical. Let's take a look at the example where hopefully this is going to be a little bit more clearer. So here we have 3 students, Jen, Kyle, and Flynn, and they're taking a bunch of different courses. If there is a line, for example, between Jen and English 105, it means that Jen is taking that particular course. Now, we're going to, first of all, try to think of how we can transform this diagram into a statement, and here's how we're going to do it. We're going to say that the statement PXY is the statement that student X is taking course Y. So, for example, the statement P Jen English 105 will mean that Jen is taking English 105 and will in this case be actually true, because there is a line connecting Jen to English 105. Notice that Jen, for example, is not taking English 110 because there is no line connecting her and that course. Take a look at the following statements, interpret them, and then determine their truth values. So the first one is, for all students X, there exists a math course Y such that that student is taking that particular course. So notice that this is for all followed by there exists, which means that we're in this first sort of game, right? For all the students, so you get to pick a student and I have to find a math course such that the student you chose is taking that particular course. Let's see, is that going to actually work for all the students and all the courses? If you pick Jen, is there a course that she's taking that is a math course? Yes, Jen is taking Math 111, so it works for Jen. If you pick Kyle, is there a math course that I can find that he's taking? Yes, Kyle is also taking 111. If you pick Flynn, is there a math course he's taking? Well, yes, he's actually taking 125 and 111. So there is a math course for any student that you can pick. And again, notice here that while all 3 of them are actually taking Math 111, that doesn't really matter. So even if that wasn't here for Flynn and he was taking Math 125, this statement would still be true. You get to pick a student, and then I get to fix the math course. It does not have to be the same math course that satisfies this requirement for every single student. They could be different math courses, okay? So this is going back to this note here. Different y's might work for different x's, okay? But because for each single student there is a math course they are taking, this statement is true. Let's take a look at the next one. Similar structure, but we've replaced math with chemistry. So for all students, there is a chemistry course that a particular student is taking. So again, we're going to go through all the students. If you pick Jen, is there a chemistry course that she's taking? Yes, 113. If you pick Kyle, is there a chemistry course he's taking? Yes, 114. If you pick Flynn, is there a chemistry course he's taking? No, he's not taking any. So this statement is going to be false, and the reason being is Flynn is not taking any chemistry courses. Okay, make sure you understand again here that different courses might work for different students. All we care about is whether or not for any given student you can find such a course. Let's take a look at this next one. There is a student X such that for all, and it's missing a word here, math courses Y, that student is taking all of the math courses. So let's read this through again carefully. There is a student X. So there is one particular student. In our case, we have one of the three choices. There is one student, maybe more, but there's at least one, such that for all the math courses, that student is taking all of them. So, is there a student that is taking all of the math courses? Is Jen taking all of the math courses? No. Is Kyle taking all of the math courses? No. Is Flynn taking all of the math courses? Yes, Flynn is in fact taking both 125 and 111, so it holds true for Flynn. And there is a student, which means that it doesn't have to be all of them, there just has to be one. And so our justification will be Flynn is taking all, or in our case both, math courses. Okay, moving along, what do we have? The next one up is there is a course X such that for all the students Y, those students are taking the course. So I can find a course so that all students are taking it. So now I have to look from the course perspective. Is there a course that every student out of the ones that we have is actually signed up for it? Is everybody taking English 105? No, Kyle is not taking it. Is everybody taking English 110? No, Jen is not taking it. And go on through all of the courses. Remember that if there exists, it means you just have to find one. So the moment you find one, you're done. So Math 125, is everybody taking Math 125? No, Jen, for example, is not taking it. Math 111, is everybody taking Math 111? Yes, bingo, everybody is in fact taking Math 111, and we can stop searching because the moment you find it is when you are done. So here the justification is everyone is taking Math 111. I really should have fixed it so that it was going to be Math 125 that everybody's taking, but so far I just have Flynn. And the last one here, for all the courses X, there is a student Y that is taking that course. So again, this is in the form like the first one, for all the courses. So that means that you get to pick a course, and I'm going to find a student that is signed up for it. And if that's true, if for every single course I can find a student that's taking it, then this statement will be true. And the moment I find a course that does not have a student signed up for it, that's when the statement is going to be false. So I'm going to go through every single course and see, is there a student taking that particular course? English 105, Jen is taking. English 110, Flynn is taking. Math 125, Flynn is taking. Math 111, again, for example, Flynn is taking. It says there is a student, so it doesn't have to be any fixed student, can be any one of them. Chemistry 113, Jen is taking. Chemistry 114, Kyle is taking. So no matter what course you choose, I can find a student that is signed up in that course. So this statement is true, and our justification here, or basically another way to rephrase this statement, is all courses have students in them. So notice that for each single one of these expressions, order matters, and the way that you interpret it will depend on the order. So be careful about those, but we will do a few more examples to see how they work out. Let's consider another example to see how the order matters. So I start with some more English propositions, let's say, more language inspired. For all persons X, there exists a person Y such that X loves Y. So remember the game, if it starts with a universal quantifier, you get to pick a person X, and afterwards I get to pick a person Y so that your person loves the person that I chose, right? There might be different Ys that work for different X's, but no matter what person you choose first, I will be able to find someone who loves them. So in colloquial English, this for all person, we normally say everybody because it doesn't matter who you pick, so this will work for everybody. And there exists a person because there has to be a more unique person is going to be somebody. So putting this all together, this first statement is going to be everybody loves somebody. Let's take a look at the second part now that has the exact same statement, except for my quantifiers have been swapped. So I start with a fixed person, X, so my somebody. And after that, so this person is pretty special because once I fix them, the rest of the statement says that everybody will love them. So there's this special somebody so that everybody loves them, or rather is loved by them. So somebody loves everybody. Right here, the order also matters in the actual way we say it. So this somebody is my X, and once you pick them, they will end up loving everybody else. Let's take a look at the mathematical statements involving multiple quantifiers. So notice that throughout these two examples, I have the notation for R star. R star represents all the real numbers except for 0. 0 is different when it comes to multiplication. So this is why this notation is actually quite standard, because we often want to talk about everything but 0, so we avoid, for example, divisibility by 0. So here we have universal followed by existential. For all x's in real numbers, so for any real number x, there exists a number y, so that x times y equals 1. So you get to pick an x, except for 0, you can't pick 0, but no matter what x you pick, let's say you pick 5, I will be able to find y such that your x times my y is equal to 1. Okay, well for 5, it's going to be 1/5. But it says that that can happen for any single x that you pick. So if you pick, let's say, 17, I will still be able to find y, so that together with the product of your x's, I will get a 1. And you already can see a pattern. Indeed, what this statement is saying is that multiplicative inverses exist for all non-zero numbers. So let me write down the procedure first that I follow to arrive at that conclusion. You pick an x, and then I can find y such that the property holds x times y equals 1. Now, this property is what we call multiplicative inverse, right? So you pick a number, again, let's say 5, and I can find the number that goes with it, so their product is 1. And this number is called the multiplicative inverse of the other number. I'm going to write this out, although you don't have to know the actual definition of the multiplicative inverse. What this is, though, saying mathematically is that multiplicative inverses exist for all non-zero numbers. This actually raises another question of, so let's say you pick a 5. Is this number that I'm going to pick going to be unique or not? Is there more than one y that will work for any single number that you choose? So for example, in the case of the people, if you pick a person, does that mean that there's only exactly one other person that they love, right? Here, if you pick a number, does that mean that there is exactly one number that will, in the product, produce a 1? So for people, maybe not. For these numbers, it's actually true. This multiplicative inverse is unique. And in fact, that there's a symbol that we're not going to use, but I think that for fullness, I should mention it. If you want to specify the fact that not only does there exist such a number, but it's unique, the symbol for that is going to be our existential symbol, followed by an exclamation mark. There exists exactly one. It's a unique y, okay? For the next example, we have, again, exactly the same thing, but the order of the quantifiers has been swapped. So the game changes, and therefore the truthfulness or the falsity of the actual statement might change. So this is saying that there exists a y, a very special number y, so that for all x's that you can choose afterwards, the product will be 1. So there's some very special number so that no matter what you throw at it in terms of multiplication, it will produce 1 as a result. Is there such a special number so that you multiply it by anything and you get a 1 back? No, there isn't. So there is no such y. No x can work No, x can work for any choice of y. And therefore, this particular statement is going to be false, right? So I can actually say that, yes, this is true, and this is going to be false. Notice that the fixing of the actual number here is what produced the problem. If this statement was, there is a special number y such that for all x, x times y is equal to x, then my conclusion would have been different. There is a special number y, so that multiplying anything by it will give you the thing back. And that number is 1. If I multiply anything times 1, I'll get my thing back. But I'll never be able to, for any number, choose another number that in the product will give me a 1 altogether. Okay? So be careful about the actual details of the questions. Once we have our multiple quantifier statements, we can think about doing other things with them. For example, negating. Now, negating is actually quite easy. We've already noticed that the for all and there exists essentially have a opposite meaning, and that's exactly what the negation will do. So in the negation, for all will turn into there exists, and there exists will turn into for all. So here, if we start with for all x, then the negation will be there exists an x. And now you just have to make sure that you actually negate throughout. So there exists a y means for all y. In E, we have that the property P holds, but you're negating throughout, so you have to negate the property as well, such that not P, X, Y. And the same the other way around. We flip the quantifiers and we negate the proposition. So for all x in D, there exists y in E such that not P of x, y. Negations, in this case, are kind of straightforward. Now, of course, we've also noticed that switching of the order will really change the meaning, and it seems that especially if you negate the actual proposition, it will switch the meaning to exactly the opposite. So let's take a look at this next example where we're asked to write negations of all the following statements and determine which one is true, the original statement you started with or the negation that we're going to produce. So my sort of universe here that I live in are numbers -2, -1, 0, 1, and 2. So I have a very specific set of numbers I'm working with. The first statement that we start with is for all x, so no matter what x you pick, I will be able to find a y such that x plus y is equal to 1. The thing to remember here is I am only working with these numbers. I don't have all the integers in my possession. I'm only working with the ones that are inside here. So no matter what x you pick, I'll be able to find such a y. Is that true? Well, let's see. No matter what x you pick, so for example, let's start going through them one by one. If you pick -2, is there anything in this set so that -2 plus y is going to be equal to 1? Well, this is a pretty simple equation that I can solve. I'm going to move over to the right-hand side. I can see that the only y that satisfies this equation is y equals 3, and that unfortunately is not in my set. So if you pick x to be -2, I won't be able to find a y that belongs in this set, right? So in other words, I can say that if you choose x equals -2, there does not exist the y such that x plus y is equal to 1. Again, remember, my x's and y's are restricted to lying within this specific domain. So this statement, as stated, is false, which means that its negation will be true. So let's go through and negate it. Remember, negating, we're simply going to go through and negate everything in our path. So for negation, we're going to have there exists an x in D such that for all y in E, x plus y is not equal to 1. Remember, we also have to negate the actual proposition. Now, again, because the original was false, this one is guaranteed to be true. Next up, we have there exists an x in D, so there is an element here, a very special element, so that for all y in E, and pardon the typo here, there should be no minus, x plus y is equal to y. So there's a very special element here, so that no matter what else you pick, I can guarantee that my choice of the special element plus your choice of any y will produce y as a sum. Okay? And yes, I claim that there is. This very special x is going to be x equals 0. No matter what you pick, if x is equal to 0, then adding it to your any choice of y will give me that 0 plus y is equal to y. So this statement is true, which means that its negation is going to be false, and I know that right away, but let's negate through. So I'm going to have for all x in D, there exists y in E, such that x plus y is not equal to y. Great. Now, I strongly recommend you pause here and try to do the other two yourself, because they will be similar in nature to the first two, so that you can get extra practice and then get feedback on how you did as I go through the examples together. All right, so we have for all x in D, there exists a y such that x times y is greater or equal than y. So I have that no matter what x you pick, there will always be a y, so that in the product together, the product will be bigger than the actual y that you chose. Is that true? Well, let's see. If it's for all x, that means I have to go through all of them one at a time. So if I choose x to be -2, is there a y so that in the product is going to be greater or equal than y itself? Well, sure, if x is -2 and y is 1, -2 times well, if x is -2, then I can choose y to be -1, then their product is going to be 2, which is greater or equal than y. And you can go through the rest of them in a similar fashion. If x is -1, I can choose y to be -1. Remember that nothing says that they have to be distinct. And then 1 times 1, -1 times -1 is going to be 1, which is going to be greater or equal than -1, which is y. And so on and so forth. So I believe that this statement is actually going to be true, which means that its negation, is going to be false. So there exists an x in D such that for all y in E, x times y is less than or equal than y. And the last one here, there exists an x in D so that for all the values y, x is less than or equal than y. So there is a very special element in this set so that no matter what y you pick, my element is going to be smaller than or equal to that. So this is essentially saying there is the smallest element in the set. And that's of course true. X can be -2. Once I get that x is -2, no matter what y you pick, my x in here is going to be less than or equal to your chosen y. So this is true, which means the negation will be false. So I'm going to have for all x in D, there exists y in E such that x is greater or equal than y. Now, considering that we've already done a bunch of examples, I strongly recommend, actually I insist, that you pause the video here and try to do these two examples by yourself. It really does help when you go through it yourself first, see what your struggles are, and then watch the video, as opposed to watching the video and lulling yourself into thinking that you understand, whereas what you understand is when someone's explaining, but not when you do it by yourself. So pause the video and then come back and we'll go through this together. So in this case, we're asked to determine whether the statement is true, false, and explain. So what I have here is for the universe of real numbers. Saying that basically allows me to not say x belongs to reals and y belongs to reals. I know that I am just working within the reals altogether. So this says that for all x, there exists a y such that x plus y is 0. So remember the game. You get to pick the x, and I can pick the y for that x so that together they add up to 0. Let's say you pick a 5. Can I find a number so that 5 plus that number is equal to 0? Remember, I am working within reals, so my numbers are allowed to be negative. Don't discriminate against those. So yes, I can pick a -5. And in fact, no matter what number you give me, I can pick the negative of it to be able to satisfy this equation. So yes, that is true. For any x in terms of real numbers, for any real number x, there is an additive inverse, is what we actually call this. Again, you don't have to know the terminology for that. You can simply say, I can negate, and together those numbers will actually produce 0 as the sum. I wrote and because that's the only thing we can actually justify for now, but it's actually the additive inverse because, again, this is where I'm going to have there exists a unique y so that this property actually holds. Let's take a look at this next one, where all I've done is swap the order of the two. What I have is there exists an x, so there is some very special x, so that for all y, the sum of the two is going to be 0. So the key difference here is that once you fix the x, this has to work for all other y's. The exact same x has to work no matter what y you choose to plug in. And that, of course, is not the case. There is no way I can find a number so that in the sum with any other number, it produces a 0. Okay, you can feel free to write out the sentence by yourself. Next up, we have for integers m and n arguing that mn is odd, then m and n are odd, proves that if m or n is even, then mn is even. That's a little wordy, isn't it? Let's try to split this up into portions. So I have integers, m and n, so my universe is now not real numbers, but rather integers. And it's saying that arguing for something proves something else. So what I actually have are two different arguments. I have this argument, if mn is odd, then m and n are odd. And I have a second argument that says if m or n is even, then mn is even. So what do I have here? Can I somehow see the structural similarities or differences between these two arguments? Here I start with claiming mn is odd, and here the oddness or evenness of mn appears in the second half, and it actually says mn is even. So my first portion traveled to the second portion and got flipped, and here in the conclusion I had m and n are odd, whereas here that turns into the premise, and becomes or, and odd becomes even. So I have a very strong suspicion that these two are in fact contrapositives of each other. Doesn't that make you realize how much cleaner symbolic logic is? Remember that contrapositive, so if my first statement here is P implies Q, then my next statement is not Q implies not P. Contrapositives are logically equivalent, and therefore these arguments are actually the same. But stating them in symbolic form makes it very clear what the structure is, whereas writing it out in English actually obscures things. So if it's easier for you, rewrite them in this format first, where you identify specifically what P and Q are, and then you're going to be able to see how they are actually the same in the contrapositive. For real numbers, write a true statement beginning with for all x, there exists a y, and the second one is the other way around. So for there exists an x such that for all y. I'm going to write my choice of statements. Your statements are almost certainly going to be different if you've written them by yourself, because there's no way that the same example popped into our heads. So for all x, there exists y. That means that you are going to give me x, and I am going to be able to come up with y so that some property holds. Well, I can actually probably come up with something very similar to this. No matter what x you pick, I will be able to find y such that x plus y is equal to 13. Okay? You pick an x, minus 7. I can find a y such that minus 7 plus my y is equal to 13. The next one, there is x so that for all y. So this is kind of what failed here. I have to be able to find a very special x so that for all y some property holds. So what can that special x be and what can that property be so that works? Well, again, there are many examples, but for example, here is one. There exists a very special x so that for all y, the product is 0. And that very special x is itself 0. No problems there, right? Try to come up with more examples of this, because coming up with examples on your own will actually solidify the differences between for all there exists and there exists to for all. The last example in this section is in the format of everybody loves somebody type thing, where I actually have a very specific proposition, and we're going to go through all the possible ways that we can quantify it with universal and existential quantifier. So what do I have? Person X accidentally bumps into person Y on the train, and that is how we define BXY as a proposition. So this means that the person X bumped into the person Y. Consider the following statements under the assumption that the quantifiers range over all the people on a very busy New York subway train on Monday morning. So it's a little bit, it can be a little bit crazy or it can be completely empty. So what do we have here? On the left-hand side, we have quantified propositions, and on the right-hand side, we have descriptions of them in English. Again, I strongly recommend you take a minute and try to actually match these up. They do match 1 for 1. There isn't one where the corresponding English version does not exist. So pause and then come back later. Okay, so let's maybe start with the first one. There exists an X and there exists a Y. So there exists a person X and there exists a person Y. So somebody here, remember, there exists in terms of people, can be translated as somebody. There exists a somebody and there exists a second somebody, so that the first person bumps into them accidentally. So I found essentially two people that bump into each other. Looking down my list, this is likely, unfortunately, it happens, corresponding to one collision. Not a big deal. Next up, we have, there exists an X, so that for all Y's, that person bumped into everybody. So there exists somebody so special that they have managed to bump into every single other person on the train. Going down the list, it's pretty clear that we have a superklutz on our hands. Next, for all X's, so no matter what person you find, I will find you another person so that your person bumped into mine, right? No matter who you pick, there will be someone that they bumped into. Okay, so what can that be? It's probably going to be extremely crowded train, because no matter who you pick, I will find someone for which the collision has happened. Let's see here. For all X and all Y, the collisions happened. So no matter who you pick, for every single person you picked, they've bumped into every single other person. They're like little molecules bump into literally every other molecule that is present. And this is generally what we call chaos. This also might represent an empty train, so nobody bumped into anybody, because otherwise that will create exponentially many collisions. There is a Y, so the second person, so that for all X's, someone bumped into them, right? So there is someone very special so that everybody else bumped into them. That's likely that they were in everybody's way and therefore simply blocking the exit. And although I don't actually like thinking that I've done everything up until now correctly, I only have one choice on the left and one choice on the right, I'd still want to reason it out. First of all, to be sure that I didn't make a mistake above, and second, to explain it. So what do we have here? We have that for every person that is the second person, there exists someone who bumps into them, right? So no matter who you are on the train, somebody will have bumped into you. And that is what here is called universal suffering. I recommend that you take a look at these and compare what you think is the case to what I have identified as the case. And in particular, maybe focus on things like chaos train versus this last universal, what I called universal suffering train. Universal suffering because it's like no matter who you are, somebody would have bumped into you. So you sort of had no choice. There was no way you were going to go out of the train without any bruises, right? But how are these two different? And how does the order, once again, of the quantifiers affects the outcome? Take a look at this. Multiple quantifiers require multiple practices, so this is a good place to start.